Hello everyone. Hello. We are live. I hope so. Let's make a test. Do you hear me? I hope so. You are hearing me well. And let's just switch me to the slides. Okay, so hello, as I said, everyone, again, after 1 week break when I needed to take some kind of health check on myself, because we are also mechanism, so we need sometimes to make health checks on ourselves. I'm super happy I'm here back after this 1 week break, and today we will cover sweep phase. So as always, say hello, say from where you are, because it is super awesome to see from where you are from all around the place and around the world. And that's all from the organization. And one more thing, as always, feel invited to ask questions. There are no bad questions. You should always ask questions. It is kind of feedback and interactive way of doing webinars. So any question is super welcome. I will try to answer immediately, or if I will not know the answer, for example, I will just say that I will find out and answer somewhere else, yeah. So today we are covering the sweep phase, and we are somewhere in the middle of the whole .NET GC internals webinars series, mini-series, and we so far covered the parts that are kind of prerequisites, so they are gathering information about what is needed and how we should garbage collect, what we should garbage collect, and so on and so on. So in the end, the answer is what is eligable for collection, and this is all about mark phase, concurrent mark phase. We covered that. There was a plan phase, which is also used somehow in all this pipeline, and today we are moving to the very first phase when something really like garbage collection happens. So all the previous parts were about gathering information, and now we want to reclaim somehow memory after those objects that are no longer needed. And we have this decision whether it will be sweep phase or maybe we do compacting, and yeah, that's those two main ways that we can do, and today we cover sweep phase. This webinar may be a little bit smaller because this is not super rocket science and the sweep phase is pretty easy, although there are some interesting things to point out, so you will see. Okay, so without further delays, hello from Ukraine, Turkey, Armenia, India, so, and one again from Turkey. So super nice to hear you all. So sweep is one of the ways how we can get rid of objects that are no longer needed. I covered that a little in the introduction. And so in the end, the goal is that all no longer reachable objects must be turned into kind of free space. That's the goal of the sweeping. So without any super complex moving of objects or anything, we are just using this information that, okay, we had this continuous memory region of objects, we marked what is reachable, so we know now that the C and F objects are not reachable, which means they are eligable for collection as it is called. And how we can garbage collect memory after them, we can somehow turn them into a free space that will be somehow reused. And this is the whole goal of the sweep, which is pretty, at least conceptually, easy, because that's the whole algorithm in one slide. In .NET GC terminology, it means simple. We can say that it is transforming all or some gaps into free list items, and we covered the gap term last 2 weeks ago. So every group of no longer reachable objects is treated as a gap, which means there are objects no longer needed, and we now are turning those gaps into something we will be calling free list items or free free item lists. It depends how you would like to call it, but in general we would like to have a kind of list that will just contain all those items of free space that may be later on used, and it may be later on used by allocators, various allocators, and for example, maybe I will not dig into that. In general, this free space may be reused, and the allocators will be interested in reusing this indent fragmentation to make use of this free space and allocate something there. So we need this free list item for that. But before we move on into all this story about sweeping, I would like to take a short stop here, because at this moment we may be a little bit confused about all those building blocks like mark, plan, sweep, compact, what happens where and what is the relation. We have this additional level of complexity, which is what is concurrent, what is not. So I thought it may be nice to give you a kind of reminder how it all works and how it is all connected with each other. So I prepared this. There I have it. I prepared this graph workflow, however you call it, which is just description of what is happening in the GC CPP file when the garbage collection happens. And here we have those building blocks in the end that we are mostly covering in all those mini series. So imagine, I mean, you don't have to imagine because there is such a method, garbage collect, with the parameter which generation we would like to collect, and it may be triggered from various places, like from allocation, probably from allocating something or so. So it will be called at some point, which is now the point that we have triggered the GC. And there is an important decision which generation we would like to condemn. In the end, I didn't cover generation concepts yet because they are not so important in explaining all those building blocks. After all those episodes, I will just add generation concept on all of that. But here the generation concept pops out because when we are garbage collecting one generation, GC has this power to decide, okay, we would like to trigger GC of the generation 1, for example, but I see that in the whole context and the whole condition around, it would be good to make a full GC, so the generation 2, 1, and 0, and so on. So here we will be just calling this method generation to condemn, and this is all those names of methods are strict directly from the GC CPP file. So there is a method generation to condemn, which is to decide which generation should be garbage collected, and also it decides whether we should do background GC or maybe it is a good time to force blocking one, the non-concurrent one. And there is this flag that will be checked, should do blocking collection, one of the flags. And this is mostly settings driven, so if you are setting your GC as a concurrent one, the decision typically would be, okay, let's make concurrent one. If you have disabled the concurrent one and you are using non-concurrent workstation GC, for example, the decision is even simpler. You cannot force concurrent GC, it will be non-concurrent. But sometimes GC may decide to force a non-concurrent one even if the concurrent one is possible. So here is this point of decision. And after this, all the code is now know whether it is to prepare and make a concurrent GC or not. So the main workhorse of the whole GC is a method called GC1. I don't know why, but it is called like that. And there is the GC1 method, pretty big one, which is responsible for doing GC, whether it is concurrent or not. So there is this flag being checked, whether it is concurrent or not. And then if it is not concurrent, as we see here, we go the right side. And with the non-concurrent flavor, we are doing things which are non-concurrent. So there will be non-concurrent mark phase that I have covered in the second episode, and there will be plan phase that I covered 2 weeks ago. And the plan phase will be the whole thing about gathering all those stuff into gaps, plugs, and gathering all the information needed both for compacting or sweeping. And this is all happening in non-concurrent flavor. And because after the plan phase we have the whole information, we can call the decide on compacting method, which will be just the one deciding whether it is now good time to compact or not. Mostly it will be based on the fragmentation of generations and other stuff. And then there will be the decision. And if it is a compacting one, we will call those methods. So there will be relocate phase and compact phase. If it is not compacting, if it is sweeping, it will call the make free list. So this is the main method doing sweeping in case of non-concurrent GC, make free list. We will cover that soon. The second scenario is when the GC is concurrent. So we go the left side here, and as we see, the flow is less complex, let's say, because in the GC1 method is waking up the GC threads, which will be doing the background work, and this background work in those GC threads is split into two methods, background mark phase and background sweep. And background mark phase is exactly the one that I've described during the concurrent mark phase episode, which was the third one, as far as I remember. So it is the concurrent mark phase in the end, called here as a method background mark phase. And then background sweep is happening, which is using the information from the background concurrent mark phase. There is no plan phase here, as you see, so it is the difference. Plan phase is only for the non-concurrent versions of the GC, non-concurrent calls of the GC. And we will cover this sweeping today, which will be covering both the scenario when the GC, it is a concurrent GC, so we will be looking at this particular block, and when it is non-concurrent, which we will be looking at this make free lists part of the GC sweeping, non-concurrent sweeping. So this is the whole graph describing how all those pieces are working together. During the next episode we will be covering compacting, because it is the compacting here. So we have a relocate compact phase, and we will cover that in the next episodes. But this is about compacting. Today we are talking about sweeping, and this graph, I hope, explains some context that you can have this non-concurrent sweeping and concurrent sweeping, which are a little bit different. And I will cover that both soon. Question is, let's just check this, whether it is working. One question: why need to separate garbage collector to generations? First of all, we don't need to do that. There are non-generational GCs on the market. Pretty popular recent GCs in the JVM world are non-generational. But the generation in the end is a more general concept of splitting the whole heap, the whole managed heap, into some smaller regions, so we can handle them in a different manner. We can handle them separately. Not everything needs to be handled at the same time. So by splitting things into smaller parts, we can handle, for example, only this particular part, not being interested in the rest of the managed heap. In the case of .NET GC, we have the concept of generations. So we are splitting all objects that we have into generations, because most typically we will be, for example, interested in looking at objects in the young generations, and less frequently we will be interested in looking at objects that are gathering in the old generations. So this is kind of partitioning of the whole space to smaller regions that gives a lot of benefits like that. We can handle them in different manner, less or more frequently, and so on and so on. And the non-generational GCs are also somehow splitting memory into regions, but they are not calling them generations, but smaller parts. Various names maybe they're used, but they are also splitting the whole heap into smaller regions to handle them separately. I hope it answers your question. At least it is super fast answer to pretty complex question. There was one block there on the slide, decide if background GC or force blocking one. This block is implemented in the GC CPP file in mostly with the help of this single if. So here we have the list of all conditions that may trigger the GC being concurrent if it is at all enabled. Because if we have disabled it because we are using non-concurrent GC, obviously it will not be concurrent. But what are the conditions? Let's look in a few seconds. First of all, the condemned generation, the funny name here is and super important in the GC is the condemned generation, so is the one that eventually has been chosen to be collected. So whether the condemned generation is the max generation, which is just another way of saying if it is the full GC covering all generations. So concurrent GC will be enabled only for full GCs. And in the opposite words, we can say that the so-called ephemeral GCs like 0 or 1 GC will be not collected in a concurrent manner. There is this flag which I mentioned, which is set by the methods checking fragmentation and other conditions that may say, okay, I could make concurrent, but I don't want to, so this would be false, and then the concurrent flag will be not set. And for example, settings of the pause modes, there are called you can set those modes via GC API to temporarily enable or disable concurrent GC. So this is looking also at the settings. And if all those settings and the conditions are met, we are saying, okay, so we are going into the concurrent version of the GC. This time, this is all the per GC decision. So this is the whole story. If you are interested, you can always Google find this exactly this code into the GC CPP file and get a bigger context, but those are the main conditions that we are interested here. So we have this decision, and now let's go into the first flavor, non-concurrent sweep. So we have this part of graph which is on the right, which means that it was we are using the concurrent GC. The blocking one was not forced, so we are going into the we are going into the non-concurrent GC. So we are there was the decision, or maybe there are some settings that we are doing it in a non-concurrent way. So we are doing the mark phase as I described previously. We are doing the whole plan phase, and then the site on compacting, and let's suppose that there is a decision that we are sweeping. So what's really important here is that in case of non-concurrent sweep, we are after the plan phase. So we have the whole information that the plan phase has calculated in details described by me last 2 weeks ago. So non-concurrent sweep will be just using the knowledge from the plan phase. And if you remember, there is this concept of plug and gap pair. So we have always the plug and gap treated together as a pair. And then we simply go plug and gap pair by one. So every pair by pair. And for every gap, we are using this gap as a free list item if it is bigger than the minimum object size doubled, simply. For smaller ones, we are not interested in such small pieces of free space, and the overall cost of handling threading the free list for them and so all will just overwhelm the benefits of having such a small free space to be reused. So we are just discarding the smaller gaps, and for gaps that are at least minimum object size doubled, which is 24 bytes multiplied by 2, which is 48 bytes in case of 64-bit runtime, we will create a free list item from it to remember, okay, here is a free space to be reused. If you remember the plan phase from the previous episode, there is this magic of handling pre and post plugs. Now it is a perfect time to recover all this space that we have made with those pre and post plugs. So we will do that, and some, as always, additional bookkeeping, like calculating the resulting fragmentation and other bookkeeping required by the GC internally. Not so important. Not so important at this point. Okay, and so just having as an example from the previous episode, imagine that we have this kind of set of objects and we are after the plan phase. So let's just enable my magic pen. So we have gaps, plugs, and so on. There is this information for every such a pair, like gap and plug. We have this information stored in the preceding space, what is the size of the gap, and that's the important information for that for this scenario. Also, though, there are those pre and post plugs that were just saved somewhere else, and to not destroy the information that we have overwritten for the need of handling all this planning. And then we are just simply doing from that single linked list of free space. We can say that in terms easy to understand. So imagine here we have a gap, but it is smaller than minimum size of object doubled. 2 times minimum object size is it's 48 bytes. I don't want to draw so let's just check why I'm drawing so thick. So it is 2 minimum object size is in the end 48 bytes. So everything that is bigger or equal than this value will be turned into the free list item. And because this gap is smaller, has only 24 bytes, we are just discarding this information. We are no longer interested in this free space. We are simply doing nothing with this because it is not big enough to be interested in it. Then from this gap we are doing the free space, and this is just turned into the free space by. First of all, we are changing the method table, because this method table is just a pointer to a metadata of the first object at the beginning of this gap. Now no longer absolutely we don't need this information, so we are overwriting it with the special method table of a free object. So there is special free object type inside the runtime, which is special pointers to the metadata of free space, let's say. So here we have this free object meta table being overwritten. Then we reuse the information about the gap size, because as we remember it was there inside the gap plug pair info. So we know this gap has a 56 bytes. So we are just storing this information after the meta table pointer, and free space is like an array. So in general it is treated as an array of free bytes. That's why it has an organization of an array, we can say almost like that. So the first field after the meta table is the size of it in terms of number of elements, but the elements are bytes, so in the end it is just information that this free space is with this size. And then we are also storing the pointer to the next free space. And because of this, all this is called threading, threading, not like in multi-threading, by threading like by interleaving or making things linked together or so. So we are threading the linked single linked list of free space items. And now this free space will point to the next free space, the free space, this one will point to the next one, and so on and so on. We are threading from every gap information about the next free space that it is there, which is, as you probably see, pretty simple. There is if you have any question, do not hesitate to ask. I see your question, Islam, about the synchronization in the concurrent case, but I will cover concurrent phase in a few slides, so let's postpone this question for a second. So I hope it is easy enough to understand, like maybe not easy enough is a bad wording, but it is easy simply to get the overall idea. And what is one important side note is what is happening with this data here. And the important fact is that nothing happens to this data. Like we don't do anything with the data that was there because we don't care. We only need to store the information that there is a free space that in future may be reused by allocator by allocating something, but it is not being allocated currently, so we don't bother about zeroing it and prepare it to be in a fresh state in the future. If someone will be interested in using it, it will probably zero this memory to have a fresh state and not the garbage inside, but it will be only if it will be reused. And now we are not zeroing anything. So in the end here, okay, we override some data at the beginning, but here we will have the garbage after the objects that there were living there. So if you have a big gap, like 1 megabyte, because it may happen in large object heap also, and we are making or it is just a lot of objects being no longer needed, so we have a big gap inside the small object heap. We are storing this information at the very beginning, like this method table, like the size, and so on, and here we are just doing nothing with that. There will be just this garbage still available in the memory. If we will take a memory dump, you will see content of strings being there, for example, because we are just doing nothing with all this stuff here at this moment. Sorry. That's a pretty wise decision, because we don't care now about what will happen with all this data in the future. And it was about small object heap. In case of large object heap, situation is similar, very similar, but as we said last time, there is no plan phase for large typically there is no plan phase for large object heap, because typically there is no compacting of large object heap. It needs to be kind of triggered, and if it is not triggered, there is no plan phase for large object heap, and so there is no data resulting from the plan phase. sorry, sometimes I make a break because I see a question and I immediately want to read it. So yes, so in the plan phase for large object heap is exactly the same, but we don't plan. We simply go by object because objects are there big enough to not group them into gaps and all those plugs and bricks. We don't care about all that stuff, but we are just creating gaps and the free items we exactly with the same approach, but by scanning objects by objects without the whole concept of the of the plugs and gaps. And the question is a very good one that from Mert, if I'm spelling it correctly. Yes, this is the second reason. So are we not compacting the minimum object size objects because there would be no enough space to hold this free object metadata size and the pointer in the end also? So yes, it is good to have this because if we have this condition always met, we will at least have the space for the size, and maybe the size would be covered by the minimum size because the minimum size of the object is at least one pointer size data field added additionally and artificially, but then there is this pointer also. So yes, this is the reason, additional good reason to not handle it and don't care about such small objects, gaps. And so this was the large object heap, and this is all about non-concurrent sweep in the end, because it is pretty conceptually easy thing to grasp. I will cover and how those free space lists, free items are used in the episode about allocations. I don't want to mix too many knowledge at the same time. So at this point we just stop at this knowledge which that sweeping is creating these free space items, and they will be used by allocators, and this will be covered in the following episodes. And the question is another question, cleaning sensitive data as fast as possible. Yes, that's pretty tough topic, because if you would like to need it, you just need to, for example, if you have a string with sensitive data before, there is no other way to clean it instead. Like, sorry, but there is no good way of forcing cleaning it. Like, as you saw, it will be left as an unreachable object flying around, and it will be in the memory. After some time after some time the GC will kick in. Then if the sweeping will be decided, it will be just there even after the GC flying around. This memory will be there even after the GC. That's why the secure string and other more complex things are for storing data that you are really afraid of keeping inside memory. That you can read from memory dump, for example. Okay. So we have covered non-concurrent, and now we have concurrent sweep, which is this left part of this graph, which is all about background merge phase. So first of all, the most important finding, there is no plan phase. So maybe from the previous episode you can have this feeling that the plan phase is always there, but even in both in the concurrent and non-concurrent flavor, but that's not the case. The correct way is saying of that is that the plan phase is only for the non-concurrent. For the concurrent, we are not doing planning, at least now. And why is that? Because currently the concurrent GC is not compacting. This the characteristic of the current GC in the .NET. So if we are not compacting in case of concurrent GC, there is no decision whether we will compact, so we don't need to plan everything, because the decision is obvious, we will be sweeping. And for sweeping we don't need all these sophisticated data that are calculated in the plan phase. That's because of that the current implementation here is simpler, because there will be always sweeping. We don't need the plan phase, so we are doing the background mark phase, and as I said it previously, it is exactly the one that I covered in this third episode, concurrent mark phase, and its goal is to populate the mark array, or also known as mark list. So it's simply storing the information what is reachable in the mark array, and then the background sweep will kick in. And that's the two phase of a simple, at least simple implementation of the concurrent sweep. How this background sweep is working: so after the background mark phase, we have populated all the data in the mark array, and the background sweep kicks in, and the background sweep is pretty similar to something which is being done in the non-concurrent plan phase, because it is just scanning object by object to group those which are non-reachable into gaps and treat those gaps into free list items. So in the end it is exactly the same, but something like reusing the data from the plan phase but without the plan phase. We are simply in the concurrent sweep scanning object by object, looking at the mark array stored somewhere else, discovering objects that are reachable, omitting them, grouping those which are non-reachable into gaps, but they are immediately threaded into the free list item because we don't need to store any gap info. We are just immediately threading all those groups of unreachable objects into free list items. So it is exactly the same conceptually, but this is happening during the application regular work, which is may seem as a little bit confusing. Like in the non-concurrent phase, everything is simpler because application is paused, everything is postponed, so nothing will interrupt us. In case of concurrent sweep, things are a little bit more complex because the application is normally working and it may allocate data, so there is now the question what is all together cooperating with each other. And this I will cover now, and I hope it will answer your question, Islam, about how it is all synchronized. So if we have this simple view of the threads during the concurrent GC, and you saw this graph during the mark and concurrent mark episodes, we have here the anatomy of the concurrent GC. We covered A, B, and C. It is a concurrent mark, so A is a first initial stop the word phase. There is this B, which is, let just me use the magic pen. So it is a initial stop the word phase. Then we have the concurrent mark, which is traversing the whole object graph while the application is running. So those T1 and T2 are just the user threads doing a regular application job. So you can allocate here during all this stuff. Then we have this last catch the word, let's say, during the stop the word phase to make the final decision what is really reachable or not. And then the D kicks in, which is our concurrent sweep. This is the part that we are interested today. Concurrent sweep. Yes, covered today. And as I said, after the C, the mark array contains information what is really reachable, so which objects are marked and which objects are not in the end. So we will be sweeping concurrently with the application. So application is running, it is allocating, using objects, referencing objects between each other, and at the same time concurrently we are sweeping no longer needed data. Sweeping like I previously mentioned, by threading the free list items. It may sound a little bit dangerous, like operating on the same set of data. Here you are using objects on the same, at the same time you are sweeping some objects, but it is in the end not so, however, unsafe. Because remember that we are sweeping only no longer reachable objects, so we are only interested in these regions of free space that will be not touched in any way by the used application, because it is representing space of objects that are no longer reachable. So while a regular application will be accessing objects here, it may change references between objects and so on and so on. We are at the same time totally safe to thread the free space items, because it is just at this part which is no longer used, so it is safe. We can thread those free items without worries. So from this part it is safe. But there is another part which makes it a little bit more complex, because as I said, allocators, various allocators, let's say allocator is using these free list items which are created during sweeping, because I said this is the goal of sweeping. We are threading the gaps into the free list items. On the other hand, allocators are using those free list items, and yet another hand, we are allowing allocating, and even we are allowing the GCs, the foreground GCs during this work. So in the end, it may happen that someone will be interested in using this free space while we are just threading the information about this free space. And this is pretty complex thing that is handled by the concurrent sweep in a nice manner. So how it is being handled? How it is being handled that on one hand someone is creating the list of free items to be used, and on another hand someone is able to use this information without big or synchronization overhead. Because as always we could put a huge log around the whole free list space and we would be safe, but obviously it would just reduce the code performance a lot, and the scalability of the code. As always, lock is a good solution but not optimal one. So there is no lock around all the stuff, and it is implemented like that. When I mentioned that D here is the concurrent sweep, it is almost true, but there is one side note that it consists of 3 sub stages, let's say. So in the end we can draw it with this additional marks. The very first one, sub stage, let's call it phase number 1, is happening even before the runtime resumes threads. So just before we start to resume threads and the application is really starting to work, and before we start the concurrent sweep, we are clearing all the free lists in all generations. So it is kind of very destructive approach. We are just discarding all the information about the free space that we had, because we will be populating this information with the concurrent sweep, so we need to have a empty data that will be now filled with the new state. So we are just clearing all those free lists. This means that yes, from now allocators will be not aware of free space for a short period of time, because we have just discarded all the information about the free space, and in a millisecond we will be just resuming all the threads, so the allocation may start to happen. And if they will start to happen, maybe we'll be interested to allocate something and need to find a new space for this allocation. And we have just cleared all the information about the free space. So yes, this means that for a short period of time, we will be allocating somewhere else at the end of the already consumed space without trying to reuse the already existing free space, because we don't know where this free space is. This is not huge problem because it is very short time, it is happening not so often, so this overhead is, and we are not even finding this free space so often, so the chance that it will happen is not so super big. So after this we have the second sub phase. Phase number 2, concurrent sweep of generation 0 and 1. So now we are just concurrent sweeping the so-called ephemeral generations, the smaller one, generation 0 and 1. And here when this is happening, when we are concurrently sweeping it, it is operating on a temporary free list. So the state is that the real free list is still empty, and we are operating it here on the special on the side created temporary free list. And this temporary free list will be published when we will finish concurrent sweep here. To publish the whole situation, the whole knowledge at the same moment, not to produce any partial data, but if it will be published, we will contain the whole information about this free space in Gen 0 and 1. And during this phase, the foreground GC is prohibited, which means the GC will not happen here as a foreground GC. It will just add too much complexity to allow it at this stage, which may, for example, try to compact the same generation while we are trying to traverse it now to thread the free list items. So it is just prohibited at this small amount of time. And when it is finished and when we publish this free list item of Gen 0 and 1, the Gen 0 and 1 will start to use it if there will be need for that. And then the last stage is concurrent sweep of the Gen 2 and large object heap, because this one is super fast because it is just clearing the free list items. This one is super fast also because it is just concurrent sweep of not so big memory region of 0 and 1 gen. And this one is the longest one. Typically it is, I don't know, 18% of the whole time, because we are just concurrently sweeping the generation 2 and large object heap, which may be really huge. And this is the most beneficial for us to do it concurrently. And this is operating on the main free list. So this is something that may be a little bit confusing because we are populating the main free list while concurrently sweeping these generations. And on the other hand, if foreground GC will happen, for example, and we will like to find a space for an object in generation 2, for a plug in generation 2 that is promoted from generation 1, we will just use the already added free list items. So we will not have the full knowledge, but we will try to use it as we know it at this moment. So the foreground GC, which will try, for example, the compacting foreground GC that will try to move a group of objects, which is called plug, from generation 1 to 2, will use this free list that is being threaded during the concurrent sweep. This is safe and without asynchronization overhead because background GC is suspended for the time of the foreground GC. So there is no problem that something at the same exactly point in time will try to use a list which is at the same time modified. There is a point that the background GC is suspended, so we know the free list item list state at this moment. We can try to use one of the elements from there and during foreground GC, for example, and then resume, and we will start to populate the free item list again and again with more data during the concurrent sweep. It is not super easy to grasp probably when I'm trying to explain it. If you find it interesting, I invite you to watch the recording or the slides, try to reread it many times, try to imagine how it is all cooperating with each other, that it is in a safe manner without any locks, with some overheads, with some compromises, but still with a pretty nice final solution, how it all cooperates. And one important remark here is also that during the concurrent sweep of Gen 2 and large object heap allocations are not allowed. So during most of the time here, most of the D phase, the number 3 phase, the large object heap allocations are not allowed. This is pretty deep implementation detail that may be a problem if you are allocating a lot in large object heap, or you are just relying on the speed of allocations in large object heap. You should be aware that they may be postponed because there is an ongoing concurrent sweep at this stage. Because it is not allowed, because then we would really have this multi-threaded access to the free list, because there would be on the one hand, large object heap allocations are just a regular code that will be happening and trying to reuse this list, while the same list is being changed by the concurrent sweep. So, or we could decide to use lock here, or just postpone large object heap allocations. And these large object heap allocations are not so often. In general, large object heap should be treated as a place for not so heavily often allocated objects. So the final decision was to go into that direction, to not allow large object heaps, large object heap allocations during this stage. Okay. Another question. I see a question. So background GC is suspended in all phases. Yes. Always when there is the foreground GC kicks in and there was a background GC, we are just postponing it and waiting until the foreground GC will end. Although probably we could imagine implementations that are not doing that, the final, let's say, results are good enough to not add this complexity of trying to handle this. And as I mentioned, those large object heap allocations are not allowed is not super problematic probably for you, because we are not used to write programs that are allocating a lot of data in large object heap. But it may happen that in your particular scenario you are doing that, like processing large bitmaps, PDFs, any data that has contain of big strings or arrays. So then you can hit this limitation, and because of that there are even special events, ETW or LLTNG events for that, and you can observe them to be informed that you have hit this situation, that the large object heap allocation was paused because of the background GC. So there is this pair of events. You can look at them manually from Purview, for example, or you can just rely on the GC stats report in Purview. There is a special table for large object heap allocation pauses bigger than 200 milliseconds. The drawback of this report is that this limit is hard-coded, so the threshold is 200 milliseconds. If you have a lot of pauses that are bigger than 100 milliseconds but less than 200 milliseconds, you will be not notified with the help of this report. So I'm always inviting you to look also at these events simply, whether they are happening in your application or not. Okay. And that's in the end, as far as I remember, most of it, because concurrent or even the non-concurrent sweep are not so complex, so we don't have so much data, so much information to cover this week. It is all what I wanted to show you. As always, few slides about the source code. So the graph that I showed you is pretty good map to navigate through various most important places in the GC CPP file. So if you, for example, would be interested in how the threading of the free list is happening in the non-concurrent GC, you will be looking at this method. And so on and so on. In case of non-concurrent sweep, you can look at the plan phase, which is the king of the non-concurrent GC in general. And there is this make free lists method doing exactly what I covered. And the main workhorse is their main free list in brick, which is recursively traversing the plug tree. If you remember the brick table concept, it is just going brick by brick and traversing the brick table, plug tree inside every brick to make those free items from gaps that are inside the plug tree. So make free lists in brick may be the main method if you would like to see the code of threading those items in case of non-concurrent sweep. In case of a concurrent sweep, there is a background sweep method, as I covered. It is split into the background ephemeral sweep, which is for Gen 0 and 1, and then the rest is also done inside the background sweep, which is the algorithm that I covered. The most important will be thread gap method and make unused array. Those are for creating those free items. So you can look at the thread gap method or make unused array for looking how those gaps are created. And there is creating of this free object, as I said, is in the make unused array. And it will be referencing as a method table this special hard-coded static field that is pointing to the free type of free object type, and threading the item inside allocator, because as I said, allocators are interested in having this information, where is the free space that it will be able to use for its own purposes. So those are the methods that you can be interested in looking at. And that's all. That's 16 slide, the last one. If you have any questions regarding what I covered today, or more maybe in more general about the GC in general, now it is a perfect time to ask, because that's all I wanted to say today. It was pretty, I was expecting it will be faster. It is 1 hour instead of 1 hour and a half like typically, because sweeping is conceptually pretty easy. So even with all those side notes and more complex internal implementation details, it was simply faster than previously. Okay, so if you don't have any questions, I will not prolong it any longer. It will be nice to have it perfectly 1 hour, so it may happen. So next week we will be covering the compacting. We will be covering compacting, which is much more complex, because then we need to move objects, and we have this relocate references and so on and so on. So it is incurring a lot of more memory traffic, for example. And I see we have one question. When server GC is enabled, we have one hub for each logical CPU core, right? So then when GC runs, does it run on all heaps? Yes. we have, in case of server GC, we have multiple heaps, as many as logical CPU cores or less, because we can configure that. But we will be having these multiple managed heaps, and there is no possibility that a single heap will be garbage collected. If the GC kicks in, it will start to collect all heaps at the same time in parallel, which is one of the benefits, because then those multiple cores may do it in parallel, really in parallel, by separate logical cores, collect their own parts of the heap. So it is done in most scalable way. And that's all. That's the answer. That's the answer. Okay, so thanks a lot for being with me today. See you next week at the compact phase, and as always, do not hesitate to invite your colleagues to watch about the GC. Have a nice day. Bye. And broadcast.